Hi, this time I'm showing you a little bit of MemCP code in the form of a Bayesian classifier. What is a Bayesian classifier? Well, for this I will show you some examples like you can learn. Bayesian classifiers are basically some kind of, it's not called AI, but it's something similar. Bayesian classifiers can classify things just by the occurrence of words. So the more often a word comes in a spam email, the more likely it is to predict this email as a spam. And in this case, I have learned a corpus for accounting. So I have things that will be accounted as type 35. Some things are accounted as type 20. Some things are type 60. And what you can do now is to query the MemCP. So I compile MemCP and then I run MemCP with apps Bayesian.scm. And now I can query the database. How do you classify this word with this category? And he says it is class 20 with a confidentiality of 0.5. So what it basically does is it has learned from all these examples. And for instance, I can teach him a new example. I can say this is my first birthday and type is classified to 666. Now it says learn OK, and when I refresh the list, I see this, it has learned the word birthday with class 666. It also excluded the words this is my, because they are very common English words, so they are filtered out. By the way, this is MemCP's REST API, so you can just say localhost 4321/SQL/ then the database you want to query, and then say select star from word classes. You can also do things like show tables, and then it will list you all tables. So how does this script work? And it is only 69 lines of scheme code. So it's a very compact algorithm. The first part consists of the copyright notice. We can ignore that. The second part is the scheme creation. So if we load the app first time, we check is in the list of databases already a base database, then everything is fine. Otherwise, we print out creating database and we create the database base. Then we do a show tables from base, and if it contains word classes, then everything is fine. And in the else branch, we say creating tables. And there we have our SQL string, create table word classes, partition int word text, category text, class int, count int. And we parse this SQL code with relative to the base database and execute it. Then we have a constant definition. So we have this define ignore words. And these are the most common German and English words. And we wrote them as a space-separated file, and we split them by space, so we get an array. Then we have this HTTP handler, so we override the HTTP handler for our REST server. And if we match our path scheme, like /base/ something, then we will handle this request. Otherwise, we will jump to the old handler. So this is the way all things are hooked upon each other. It's very, very, very similar to Node.js web servers. And now we have, at first, the first thing we do is, the thing after base is a word. And we can do two things with this word. We can either learn, or we can try to classify the sentence. But at first we have to split the word, so we say to lower. So we put every word in lowercase. Then we split it with spaces. Then we filter all words that are not on the ignore list, so not has ignore words word, and set the variable words to it. Now we have in words, we have our relevant words. Then we ask the HTTP query if it contains the parameter classify. And if there's a classify question, like here, we can say classify equals type. Then it will classify for the category type. So we can also make the Bayesian database learn all different kinds of classifications. Like in one thing, we want to have the mood of a sentence. Then we have to have the accounting, the account for a booking text, or we can learn whatever we want. So back to the text. So we have checked if the parameter classify is available. When it's available, then we run the classify algorithm. Otherwise, we will run the learning algorithm. Remember, we have already split our sentence into single words. Now what we do in the learn algorithm is we just push every single word into the database, and this is done here. So we map our words. Map is like a for each loop, and then we have our query. So in the learn algorithm, we can learn multiple categories at the same time. For instance, I can say, I hate you, and we say mood is bad, and content is evil. Now it has learned these things. Now we can we have these new examples learned. So the word hate, if I now ask, do you hate me? And we classify for mood. It will say it is a bad mood with a confidentiality of 0.5. Back to the code. So for every word and for every class we specify in the query, we will just insert into database base table word classes the following dictionary. Partition is 1, word is word, category is category, class is class, count is 1. So what does partition mean? Partition means we can extend the whole thing to have multiple partitions. So for instance, if one customer wants to learn with these example and another customer wants to learn with other examples, we can separate them. So that's basically it. This is how we insert our learning examples. And this is now the algorithm to calculate the sum. And this really exploits the parallelism of the the MemCP in memory database. So at first, we will scan through all the word classes. And scan has a very interesting signature. So the first parameter is the database, the second is the table. The third parameter is the filter condition. The fourth parameter is the map. And the fifth parameter is the reduce. And the sixth parameter is the neutral element. So we have, scan is like the map reduce algorithm. So this is filter, this is our filter condition, this is our map function, this is our reduce function, and this is our neutral element for reduce. Let's examine the single parts. The filter condition, now 3 filters are applied. At first, the partition must equal to 1. So for the condition, 3 columns are read: partition, word, and category. Partition has to equal 1. The word has to occur in our parsed words from the list. And the category has to equal the category we are searching for. This is the filter. Now to the map function. In the map function, we read out the columns class and count. So we have like one time 35, one time 35, one of 35, one of 35, one of 20, and so on. These are the things we are extracting for the map phase. And in the map phase, we just return those 2 values as a tuple, which means this is now shifted to the reduce function. The reduce function starts with an empty dictionary, and then we associate, then we merge all these things together. And when 2 keys, so we merge A and B together. So A is the accumulator. So A starts with this empty element, and B is the thing returned from the map function. So we combine the empty set, so the empty list, with 35 is with 1, for instance. And this merge association, this merge assoc function will combine 2 maps, so 2 dictionaries, and so it will combine dictionary A and dictionary B. And when 2 elements are with the same key, it will apply plus as the collision function, so it will add up. So for instance, when we have 35 times 1 and 35 times 1, it will add up 35 to 2. So all these counts will be added to each other. This result is stored in egg. We can try to print it out. So let's print out the immediate result AGG. And it will tell us that bad is counted with 1. And then the only thing, so let's test a different word. For instance, this word or this word. And this word has 2 examples where it's classified as 20 and 1 example where it's classified as 21. And now we have to somehow compare all these results and filter out the best one, so the one with the highest score, and then calculate the confidentiality. And the confidentiality is the sum of all these things, is this one divided by the sum of everything plus 1. Plus 1 is something like we never have 100% confidentiality. There's always the possibility that we have one virtual example that will not be classified as anything of the database. So now let's move on in the text. We have this reduce function, reduce assoc, and it will start with a start value of unknown. So if we have some unknown word, it will just say unknown. So if we have a word like say foo, it will get into the class unknown with a confidentiality of 0%. So we know it's not true. And then reduce assoc has these A. This A is the accumulator. So A will contain this unknown 0, 1 and the key and value of the next pair we get from the dictionary. At first we disassemble A into 3 variables. So A is a list with 3 elements, and we disassemble these 3 elements into the 3 variables best score, and total. And then we have if our value is better than our best score, then we will have the new key value. And of course we add the totals together, and otherwise we leave the old best score and add up the totals. After this is done with every key value pair of the result of this one, we will have the value and the best score in result. And the only thing we now have to do is, again with a match function, disintegrate the result into these 3 variables, and then say class is best and confidentiality is best score divided by total. And we can remove this to do because we already have implemented it. So this is basically the Bayesian algorithm. So we needed about 70 lines of code in Scheme. And about parallelity. this scan function has to fetch things from the in-memory database. And the in-memory database is organized into shards. So every shard is as big as is just big enough that you have a defined amount of time to completely scan it within some milliseconds. So you have a guaranteed execution time of some milliseconds for each shard to process. And then if you have the same amount as shards as CPU cores or less, then you will always hit this boundary. So you will never exceed this time boundary. So you can really talk of a real-time database that has a guaranteed response time for each query. Now, what does scan do? Scan runs separately on every shard. So at first it will map. So for every shard there's a new thread opened, and each thread scans over the database. At first, the database will try to turn this condition into a index scan, so we don't have to examine all items. We just have to filter out those items that are relevant for us. Then the map function is executed for every item, and the reduce function is started for each thread separately, and then a second reduce pass is done over all shards. So in the first phase, the shard local reduction is built. So we calculate the sums of all probabilities for one shard. And now we have like the results from 10 different shards. And now we do this reduce over the 10 immediate results of the shards. So it will, at first, all 10 threads will run in parallel, and then one thread will do like 10 aggregations to calculate the overall sum of the shard. So this will work on billions of datasets, and we already tried it with big benchmark datasets. So stay tuned with the MemCP. You see, it's like we don't use SQL here. We just use the handcrafted scheme operators and directly tweak and directly run on the database. And if we say this parse SQL, this will also create a query plan in Scheme, but we have the nice and easy to write SQL, whereas Scheme is a little bit harder to write. But the cool thing with Scheme is that it is both data and code. So everything in Scheme is like a Lisp dialect, and every value in Scheme can either be data or code. And it's just everything is built from lists. So like set old handler is a list of 3 items, set old handler HTTP handler, 3 items in this list, and I can just execute this as code, or I can store it in the database. So we can also save code and use it for later execution. Like, I don't know if you know it, like it's a similar concept like Erlang. Now, to come to a conclusion, we have a base classifier, so we can put learning examples into the database, by the learn function. And then we can ask the classifier if he knows the class of a sentence. And this way we can do classification like is the mood good or bad of a text, or is a text about buying or selling stuff, and so on. I think that's it for today. I hope you have enjoyed this episode. Of course, there are lots of tweaks to do here still. Like in the moment, all words are handled independently from another, but they are not normalized against the total amount of examples for a class. So we have to tweak this after a while. And also we insert everything into with a count of 1. Instead, we should rather do something like update count is count plus 1 if the thing already exists. But that's something for the future. In the moment, we don't need it that refined. It's just a cool Bayesian classifier, and we can use it for our next project. If you want to get involved into MemCP, MemCP is a high performance and memory database that aims to be fully compatible to MySQL, so like a drop-in replacement, but with a magnitude of performance. So if you want to join the development, check out the GitHub repository, try some SQL, and help us improving the parser and the scan operations and the index building and so on. Thank you.